Hyun Kim from Korea and right now from Yale, who's going to talk about canonical basis for moduli spaces of local systems related to higher.
Thank you for the introduction and thanks for the invitation. So it's my first time in India, so very happy to be here in this peaceful institution. Subhojoy, Gupta, and I overlapped in the graduate school. I think we didn't really talk about math that much. I have some other memories, but I shouldn't share them because I don't want to embarrass him. Anyway, so my talk will be pretty algebraic, but I'll try to make it as elementary as possible so that each of you will find something interesting out of it. It's kind of a dangerous time because it's afternoon, so it's easy to be sleepy. I'll try to make it as fun as possible. So there must be actually surfaces somewhere, so moduli space of local systems on the surface, but I sort of deleted it because it was already too long. So I should start from a surface, S, a punctured surface. So in picture, it should look something like this. And I really do need a puncture. So we don't know what to do when there's no puncture. So there must be at least one puncture. And I require the Euler characteristic to be negative. So that's not that serious a restriction. It's just saying that for genus 1, you had to have at least 3 punctures. And then the other input that I need to start the story is G, a Lie group, or algebraic group. Split reductive algebraic group. You don't have to know all these words because I'm just going to be working on examples, which is just SLN or PGLN. You don't even know what SLN and PGLN are because I'm just going to use them as symbols and I'll be looking at its algebraic structures. And so I prefer not to specify field here, but if you're not comfortable, you can just think of them as SLNC or PGLNC. So I prefer to look at them as group schemes so that you can evaluate at a field later if you want. But you can just look at SLNC and PGLNC for today's purpose. Basic space that I'm interested in is the moduli space of local system, G local systems. So let me call it loc GS. Moduli space of the so-called G local systems on S. You don't have to know what G local system is because I'm just going to say in this way and not really use that definition. A useful thing that you might have in mind is this one way of viewing this moduli space is to view it as a space of representation of the surface group. So the fundamental group going to this algebraic group G, mod out by conjugation. So I won't say so much about how to take the quotient, but anyways, this is the conjugation action. So that's like the basic space. But for some reason, for some aspect, this space by itself is kind of difficult to study. So what Fock and Goncharov did is to study certain modified version of this space. So I think I can write here. Fock and Goncharov. This was early 2000s. And then later, Goncharov and Shen. They considered certain modified versions. modified moduli spaces. Largely, there are two. One is called AGS, and the other XGS. So this was about early 2000s. I'm not going to give a precise definition. I'm just going to explore some properties that it has. But very roughly speaking, XGS is, as I said, some modified version of locGS, which is just a representation space. It's moduli space that parameterizes not just local systems, but so-called framed local system, framed G local systems are nice. So that means G local system equipped with a so-called framing. And that framing is certain extra data that you choose at each puncture. So some extra data at punctures. But again, I'm not going to give a precise definition. But the amount of extra data that you choose at each puncture is, roughly speaking, Weil group many. So it's sort of a ramified covering, like a branched covering. And so I didn't even define what this is precisely, but anyways, some way of considering some modified version, and A in a little bit of a different way. And then what they showed is that when they considered these modified moduli spaces, they showed some nice properties of these spaces. And here's one sentence that I can say. So Folk and Goncharov, they showed that whatever this is, A moduli space for SLN for a puncture surface, and X version moduli space for PGLN. They are nice in certain sense. They have, so each of them is equipped with certain coordinate charts, some nice coordinate charts. So I will be explaining what I mean by nice coordinate charts in a second. But anyways, what I can say is that so that they form an example of cluster variety, so that these spaces are not exactly, but almost birational to what is called a cluster varieties. So I will be giving definition of cluster varieties and then tell you some problems that arise from that theory in the case of ASLN and XPGLN. So in order to tell you what I mean by this sentence, so I have to tell you what I mean by the cluster structure, cluster variety structure. And for that, I have to give you some quivers, which are special graphs with orientation. So the initial data that we choose in this story is this puncture surface with either SLN or PGLN. So we chose little n and a surface. And this description of cluster variety structure needs, as I said, a quiver. So let me now describe this special quiver that I'll be using. And for that, I first need to choose what is called an ideal triangulation of the surface. name it as T, an ideal triangulation of S. So instead of trying to write down the precise mathematical definition, let me just draw it in picture. So here was the puncture surface. Then you want to triangulate the surface by simple path that connects punctures, and they may end in the same puncture. But anyways, you want to draw it so that it triangulates the surface. So the edge of T, each edge of T must connect punctures. So the vertices are punctures. That's why it's called ideal. And then everything is defined only up to isotopy, or homotopy if you like. So we have to choose one such data. If you're bored, you can compute the number of edges that you need for a genus G surface with some number of punctures. Now for each choice of ideal triangulation, I'm going to give you a special quiver. Which I write as QTN. So Q for quiver depends on T and N. This is sometimes called the N triangulation quiver, or the triangulation. So it looks as follows. If you choose a triangulation, then it consists of the edges, and then it divides the surface into ideal triangles. And for each ideal triangle, so here's a triangle formed by T, you consider the following quivers. So here's what happens when n is 2. So 3 vertices, and then it goes around. This is when n is 2, and n is 3. You subdivide like this. So all these are vertices of the quiver. And the orientation is such that the small triangles, they go like that. This is the case for n is 3, which is used for SL3 and PGL3. And you can go on. Like for n is 4, you have to use that, and then you can give orientations as I did. So you do it for every triangle, and then you put them together to get a single quiver. So for each choice of ideal triangulation, you get one complicated looking quiver. So what I just said is that your ideal triangulation consists of a bunch of triangles, and then you would do what I did there. And let's say for n is 3, you do it for every triangle, and then blue. Then you get some quiver that I call this. So let me give you an example. So as an example, yeah. No, so these are quivers. So quiver is directed graph. So graph with each edge oriented. So a bunch of vertices and bunch of arrows between vertices. No, no. So for here, you're only seeing, this is the quiver. So I'm going to give you an example. Right? So directed graph. So when n is 2, and when the surface is once punctured torus, then whatever triangulation you choose, the resulting two triangulation quiver has 3 vertices because the triangulation has 3 edges. When n is 2, there are 1 quiver vertex per each ideal edge. There are 3 vertices in total, and the arrows go this way, like that, sometimes called a Markov quiver. If you do the same thing for one puncture torus for n is 3, then I'm not going to give you a picture. The same one puncture torus. Then this thing is some quiver that consists of 8 vertices. Right, so the original ideal vertex, which are punctures, they are not part of the quiver. So it's sort of a graph that's drawn on the surface, on this puncture surface. But of course, you can take the combinatorics only. So I just defined some special quiver after I chose an ideal triangulation. And then what Fock and Goncharov did is that for each vertex, let's say little v of this quiver, they constructed some coordinate function on the moduli spaces. Fock and Goncharov, they constructed some coordinate functions. So they did it for each ASLN and XPGLN. So let me give different notations. So A small v on this ASLN moduli space, whatever this is. And for X, let me call it big X, V, P, GLS, GLNS. Three edges for triangulation. So the triangulation would look something like this. Right. So for n is 3, but this vertex is the same as this vertex. This is the same as this, and so on. So here is 7 plus 1. The arrow goes like that. So sometimes there's some cancellation of arrows, and sometimes there are addition of arrows, and whatever quiver you get out of that is my quiver. Yeah, any chosen triangulation gives you one quiver. That's right. So I'll get to that. Right. Yes, but at this point, so for any chosen triangulation, you can just think of the vertices of the quiver, just some combinatorial set, and then so they used the data of ideal triangulation to construct this many functions, and the theorem is that they form a coordinate system. So let me write the statement down and then explain it more. One theorem by Goncharov, which was publication year is 2006, I believe. So for every choice of ideal triangulation, these coordinate functions, these functions yield birational maps. Meaning that they're not exactly bijection, but almost. So ASLNS looks like, so let me just use over C. I didn't define this vertices so each function is valued in C star, and the C star to the number of vertices is not exactly ASLN, but almost. And similarly for X, PGLN, birational 2, C star to the number of vertices of this N triangulation quiver. But I want to say more than that, so I haven't finished writing down this theorem. The theorem also says about what happens if you choose different ideal triangulation. And that's actually more important than just the statement that I wrote so far. So it's still part of this theorem. So coordinate change maps, transition maps, for charts for different ideal triangulations. They follow a special pattern called cluster mutations. So they are special compositions of, for the A case, it's called cluster A mutations. So I'll be saying what I mean by this. In the case of A SLN S, and for the X PGLNS, they follow cluster X mutations. So at the moment, this is the theorem, but I will be describing in more detail. The cluster mutations, which I will give explicit formula now, is a special rational expressions, some rational formulas, that's combinatorially defined using the quivers. So before writing their formulas, let me just say that these cluster mutations you will be seeing soon, that there are some rational coordinate change formulas combinatorially defined using the data of quivers. So here the rational is a good property because that's why it came into the realm of algebraic geometry. For example, if you think of Fenchel-Nielsen coordinate for Teichmüller space, the coordinate change formula is not rational. It involves a lot of hypercosine, hypersine, and square roots, and so on. So they're not algebraic. So you can't do algebraic geometry there, but here they are rational formulas. So that's one good property. The other remark that I should make in this conference is that these special coordinate system is how Fock and Goncharov approached the theory of higher Teichmüller space. So let me just write down a very short remark. It's that if you take the set of positive real valued points, so far I was using like SLNC, PGLNC, which means that I'm looking at C points. But if you evaluate at real, and then if you take all the points whose special coordinate values are positive real, you get some sets. And these are the Fock-Goncharov version of higher Teichmüller space. I won't be using these today, but just as a remark. So now I will give you exact definitions of cluster mutation formula. Not that I will be using it, but if I don't give that definition, then I will not be giving any specific definition today. So at least I have to give you like one complete definition. So cluster mutations. Well, if you already know something about cluster algebras and cluster varieties, so the formulas that I'm going to be giving are not the most general possible, but general enough so that it contains this ASLN and XPGLN. So we start from any quiver. So I'll be giving an example. And then not just the quiver, but at each vertex of the quiver, you can imagine you have a coordinate variable attached. So with some, let's say some formal variable, let's say AV, at vertices of the quiver. So let me draw an easy example. So let's say we are dealing with this special quiver, and each vertex has some variable attached. Let's say A1, A2, A3, A4. So that's where you start from. And then there's a special transformation rule that transforms this picture into different one. So you get different quiver and different variables attached, which is called a mutation. So you choose one vertex to mutate at. So mutation at, let's say, V. You choose some vertex, and let's mutate at that vertex. This is called mu V, mu for mutation. And for this example, let's choose to mutate at the A2. And I'm going to write down what happens. And then I'm going to give you general formula. So all the arrows at the vertex that you mutate at, you reverse. And then you have to add some arrows according to some combinatorial rule, which I'll write down. I'm just giving you this as some example that you can take a look. So some new quiver with some new variables. Let's say Q prime with new variables. New quiver means that you don't touch the set of vertices, but you only change the arrow in some way. So now I'm going to write down the formula of how to change this thing. To save time, I'm not going to give you like detailed description or reasoning. I'm just going to give you a formula. And to do that, first I want to write quiver, not by pictures, but a convenient way of recording a quiver is just by reading the adjacency matrix, just to count the number of arrows between every pair of vertices. And you do it with sign. So quiver Q, I will read its signed adjacency matrix, which following Fock and Goncharov, I will say epsilon. So for each pair of vertex, you just count the number of arrows with sign. So epsilon ij is the number of arrows from I to j minus the number of arrows from j to I. For example, from this picture, epsilon 1, 2. So I'm just labeling this as 1, 2, 3, 4. So epsilon 1, 2 is, you have 2 arrows. Epsilon 2, 1 is -2. So this way you get skew-symmetric integer-valued matrix, which is sometimes called an exchange matrix. That's the signed adjacency matrix of the quiver. So you can either work with quiver or skew-symmetric integer matrix. And now I'm going to use that epsilon ij's in my coordinate change formulas. So first, let me tell you how the quiver changes, which I call quiver mutation. Let's say that we mutate at k. So at a vertex k. The new quiver will have its signed adjacency matrix, and it's given as follows. It's not very instructive if you just look at the formula for the first time. There is a combinatorial way of saying what happens, which is easier to understand, but even that doesn't tell you why it's a natural thing to do. So just take it as definition. Some combinatorial way of changing the quiver, and then I'm going to tell you how the variables change. Cluster A mutation and cluster X mutation. First, cluster A mutation. The new variables after mutation. So in fact, only one variable changes. So everything stays the same except for the kth variable that you're mutating at. It mutates by a certain formula. As I said, I choose not to say too much about these formulas, but I'm still giving formulas because otherwise you won't see any precise definition today. So the first term is just product of all variables that's for the vertices that's incoming, that has edges that's incoming from K. And this is going to K. But whatever they are, this is some combinatorial formula. Cluster X mutation uses X variables. They look a little different. So example of cluster A mutation is Plicker coordinate, Plicker relations for Plicker coordinates for Grassmannian, or lambda length for decorated Teichmüller space. Cluster X mutation mutates like this. Some more number of variables change. So the precise formulas don't matter so much today because I'm not going to be using them seriously. But you can see that there's some rational formulas. Example being the shear coordinates for enhanced Teichmüller space. So that's like what happens for general quiver. And we'll be applying this for the special quivers that come out of the ideal triangulation. So you will apply these formulas for the n triangulation quivers. And what Fock and Goncharev did is that they found a special sequence of mutations that connect the special charts for different ideal triangulations. So for each pair of ideal triangulations, let's say T and T prime of the same puncture surface. Bok and Goncharov, they found specific sequences of mutations that relate the two coordinate systems. It's not hard to describe what these sequences are, but I'm not going to do them today. So found specific sequence of mutations connecting their special charts, which I mentioned before. Right. So let me give you an example. So I wasn't going to tell you the answer, but now you asked. We know that every two ideal triangulation are connected by flips. And by flip, I mean the change of ideal triangulation that changes exactly one edge. So it suffices to know what happens there. So let's say that you have an ideal triangulation like this, and then you change it to this different ideal triangulation by so-called flip. So you just replace this by the other ideal edge, and then you will have, let's say when n is 4, you have this complicated looking quiver whose vertices look like that. I'm not going to draw all the arrows. And then for here also, so here's a sequence of mutation. You first mutate at these 3 vertices with any order, and then you do this like kind of rectangular stuff, and then you do these. And after that sequence, you can do it by hand. I gave all the formulas, so you can check whether at least the quiver for this guy changes to this quiver. But not just the quiver, all the variables that they defined using geometry, they're related by this particular sequence of mutations. So for n is 2, it's very easy. It's just 1 mutation per each ideal triangle, each flip. Okay, so that's what they did. And I can be more general. So the Fock-Goncharov's moduli spaces, they have cluster variety structure in this sense for special quivers. But theory of cluster varieties, they work for any quiver. So we can now just be free and think of any quiver and construct some abstract cluster variety. So let me try to do it now. So conversely, given any quiver that you like, with finite number of vertices, or equivalently, you can just start with any skew-symmetric integer matrix. Now I'm going to tell you how to construct a cluster A variety and cluster X variety from this initial data. What you do is you start from what algebraic geometers would call a torus. So you can start with a split algebraic torus. In short, just torus. For them, torus is just C star to the number of some integer. So in this case, we will be using the number of vertices of the quiver. So if this quiver has m vertices, this would be C star to the m. And so each quiver with variables attached. I think I erased them. So each such picture corresponds to one torus, and each coordinate variable is the coordinates for the torus. And then we'll be gluing several tori along these cluster mutation formulas. That's what I'm going to do. But before doing that, so when I say torus, so this is like the basic thing that you will be gluing together. And for one torus, this is a scheme where the algebra of regular functions are the Laurent polynomials in your variables. So let's remember that. So algebra of, because I'll be using the word regular functions later. So algebra of regular functions on this torus is just algebra of Laurent polynomials in variables enumerated by the vertices of your quiver. So you can take it as a definition of a regular function on a torus. And then you will be gluing these different copies of tori together with formulas that look like this. And the resulting space is called a cluster variety. So what you do is you start from one torus, which is equipped with one quiver, and then you repeatedly apply cluster mutations. Let's say cluster A mutations only at the moment. And then you glue all resulting tori. This means that you start from one torus equipped with some quiver. If the quiver has m vertices, there are m ways of mutating it. So you get m different tori after mutation. And for each quiver, you can mutate again. So in general, you get infinitely many different tori. And then each of them are related by these cluster mutation formula. And then you glue them together. So after you glue, what you get is the so-called cluster A variety, which I'll write either as A of epsilon bar. Bar means mutation equivalence class of the initial matrix, or mutation equivalence class of the initial quiver. So the bar means mutation equivalence class. So anyways, you can start from any choice of quiver, any choice of skew symmetric integer matrix, and then just use this abstract combinatorial formulas to glue different tori and get some space. And if you use only cluster X mutations, what you get is cluster X variety. Yeah. If you would like, you can think in that way. Yes. I don't think so. So in today's talk, I'm not going to ask or answer such a question. So I'm only going to ask. We will be looking at its algebra of globally regular functions, and then if you want, you can take a spec of that. So that's what Fokken-Goncharov does. But I'm not going to ask more than that. But people study more questions than I do, but we can talk about it later. Typically, yes. So typically, it can be very bad in general. And likewise, if you use cluster X mutations, you get cluster X varieties, which I will denote as X of epsilon bar or X of Q bar. So now I can rewrite Fock and Goncharov's theorem in a concise manner. So Fock-Goncharov's theorem is rewritten using this language. I can now say that, let me write it here. This special moduli spaces, which I haven't really given you definition of, some modified version of the moduli space of G-local systems. So ASLNS is birational to the cluster A variety with the N triangulation quiver of your surface for any ideal triangulation. And this thing with X. So they are different spaces, but associated to the same quiver. So then now we are in the realm of cluster varieties. So we can either apply techniques or ask questions that you can ask in the theory of cluster varieties. And one of the phenomenon, I think central phenomenon in the theory of cluster varieties is some sort of duality. There's some sort of duality between A and X for the same quiver. So in some sense, they have some duality with each other. And I will be explaining one important aspect of what can be called a duality, which is called a Fock-Goncharov duality conjecture. Which was there essentially from the beginning of Fock and Goncharov's work. So they originally formulated it using for only the N triangulation quivers, but then they generalized to all quivers. So one version looks like the following. So for every quiver Q, there exists the so-called duality map. Well, now the name doesn't really matter, but I call it duality map. Boldface I associated to the quiver mutation class of the quiver that goes from the set of ZT points of the cluster A variety for this quiver. I'm going to explain what I mean by ZT. Injectively into algebra of regular functions on the X side. This is for any quiver, but if you apply for this QTN quiver, this will tell you some duality between ASLN and XPGLN. And I have to tell you what I mean by ZT and then what I mean by ZT points, and then I have to tell you what this map has to satisfy. So I'm not going to tell you everything, but only some of them, such that the image of this map which is some subset of the target, should be a basis of the target algebra. This is an algebra over C, so it's in particular a vector space. And the image of this map should form a basis that satisfies lots of nice properties. And let me even say that the image should form a canonical basis. I want to say this word because it's in the title. Basis, the canonical vector space basis of the target algebra, satisfying several properties, which I won't really go over today. And then I have to tell you at least the definition of the ZT. ZT is, so you usually would evaluate a scheme or a stack at a field, but this is a semi-field. Semi-field is something like a field without subtraction. And this is a special example. ZT is a semi-field of the so-called tropical integers. So it's just Z as a set, and it's equipped with strange addition and strange multiplication. The strange addition is minimum, and strange multiplication is the usual addition. And then you can check that they satisfy the distributed law, and you can divide. So this strange multiplication has an inverse, but there's no subtraction. It's a semi-field, and you can evaluate at a semi-field in the sense that, so the usual cluster A variety we obtained by using copies of tori along cluster A mutation maps. Now we glue copies of ZT to the M along tropicalized version of the A mutation maps. And this is possible only because the cluster mutation maps do not involve subtraction. So if you go back to your note, you see no subtraction in the formula. So this set, which appears in the domain of that duality map, is the result of gluing ZT to the number of vertices of the quiver, which is, as a set, just let's say Z to the M, along tropicalized cluster A mutations. So you take the cluster A mutation formula that we saw before, which is about formal algebraic variables, and they involve multiplication and plus and division, and replace these operations by these strange operations, then you get some tropicalized formulas. And that's what you use to glue different copies of Z to the M. And it turns out that for the semi-field case, this gluing are all bijections. So even after you glue, this as a set is just Zm. So it's just same Z to the M glued bijectively together with strange looking piecewise linear formulas. That's what I mean. It's a pretty abstract set. And the target ring is just a ring of algebra of regular functions. So let me write that also. Algebra of globally regular functions. Which means that, so we constructed X variety as by gluing different copies of tori. Each torus, the algebra regular functions, are Laurent polynomials in its variables. And in general, if you write down, take any function on one chart, write it down in terms of the variables for the next chart, it doesn't stay Laurent. But I'm saying that you should find all the functions such that it's Laurent polynomial in every chart. That's what I mean. So sometimes it's called universally Laurent functions. Because in this particular case, for each cluster chart, regular means Laurent. What's the question? Can you say again? Yes. Yes. I think that's a good viewpoint. I never view it that way, but it might be possible to relate to what you said. But at the moment, I'm not doing that. And for general quiver, it's a lot more general than that. There's nothing really you can say in general manner. But anyways, let's just be content with what I said already. And since I don't have much time, so I'll say a couple of remarks and then give you some known results and some open problems. So I said this is one version of what is called the Fock-Goncharov duality conjecture. There's another version where you replace the role, exchange the role of A and X, which is more popular for people who study cluster algebras. So I'm more of a cluster variety person. So just remark that there's also a version of this conjecture with the role of A and X reversed. And then what were of my interest for a long time is the quantum version of what I wrote. There's also a quantum version of the duality conjecture. Let's call it IQ, where little q is the quantum variable, whatever it means. The domain is the same set, but the codomain is now a ring of quantum regular functions. So instead of trying to glue commutative Laurent polynomial rings, now you glue non-commutative Laurent polynomial rings by some non-commutative mutation formulas. You glue what's called a quantum torus algebras, which are non-commutative Laurent polynomial algebras where the variables don't commute, but they q commute. They commute up to some q power. But since I don't have time, I'm not gonna write that down. So now let me give you some results. So the most original early results is already in Fock and Goncharov's first paper, which says that there exists a nice duality map for the two triangulation quiver of the surface, which means the SL2, PGL2 for puncture surface case. So i.e. some I map which looks like this, which is sort of the Teichmüller space case. So this gives you some nice basis of the ring of functions on some version of the Teichmüller space. And then in that paper, they conjectured that this should be true for higher rank SLN, PGLN, and then there must also be quantum. So they conjectured for SLN, PGLN, which means QTN, and that also their quantum versions. I have only 1 minute, so let me just write down like 2 lines. One theorem that I obtained some time ago with Dylan Allegrady, who was a student of Goncharov, is that we showed how to quantize Fock and Goncharov Fock and Goncharov's SL2 PGL2 duality map. And then more recently, I did it for 1 rank higher. So this is recent. This is going to be published somewhere in this year. Is that I constructed I and IQ for SL3, PGL3. And all of them, they use some sort of quantum topology, like skein algebras and things. And then still open problem is how to do QTN for n greater or equal to 4. I'm already out of time, but let me at least write down another result that I put it in the abstract, which comes from mirror symmetry. So in fact, so I wrote it as a problem, which sounds like it's never constructed. So that's kind of true. But its existence has been proven. The theorem by Gross, Hacking, Heel, and Savage, which is published in 18, that for any quiver, not just these n triangulation quiver, but not just any quiver satisfying certain combinatorial condition. Satisfying certain condition. There exists a canonical I, and this work uses mirror symmetry of log Calabi-Yau varieties. It's very, very powerful. And then, well, I will have to stop here, but let me just say in words. So this certain condition is usually very hard to check. And Goncharov and Shen, they checked this condition, that this condition holds for the n triangulation quiver in some paper. So now we know that it exists. And then there's a quantum version. So this basis that comes from their work is called a theta basis. And then there's a work by other people, Ben Davison and Travis Mandel, constructing quantum theta bases under the same condition. But the caveat is that the existence from mirror symmetry, it's almost never constructive. You can never write down any function. So it's not really constructive. So of course, the natural question you ask is how to connect this to all the other works that I said, which are all geometric and constructive. And more recently, Travis Mandel and Fan Chin, they proved that for Qt2, for SL2, PGL2, the mirror symmetry solutions coincide with what I wrote there. So I'll stop there. Thank you.
So I have a question. So should one think of the domain of this duality map as infinity of this A, some A cluster variety or something like that? I mean, where is this? How should I think of what was their motivation of the duality map? Where did it come from?
What was their motivation?
Yeah. So how did they come up with it?
That I don't know what their motivation was. This is different from integer points. It's more of a points at infinity. Mm-hmm. So like if you consider functions, and then if you want to study its asymptotic behavior, I'm just saying very roughly, then like if you have some Laurent polynomial function, let's say, its asymptotic behavior is dominated by either the highest degree term or the lowest degree term. And that's what this captures. So it's more of a points at infinity of something rather than integer.
So of some cluster A.
I think so. So I think they have a paper, Oak and Goncharov has one other paper that says something about that viewpoint. But I don't actually know like how they came up with this kind of framework from the beginning. They might have like motivations from different perspectives. Well, recently, it's been proven by what I just said is that there's like exactly same looking framework in the perspective of mirror symmetry of log Calabi-Yau. But a priori, this work has nothing to do with mirror symmetry. But I think they had some idea. I don't know which one was like what led to their statements and conjectures. Right, so they're more general. So what goes in here and what goes in there should be Langland's dual. Yes. I think so, but I don't have enough knowledge to say any clever statement to that. But I think it is related. And somehow A of PGL2 is not cluster. It's close to that. But you can exchange this whole thing with that. Exchange a rule. That still works. Right. And in general, this and this must be Langland's dual to each other. I only focus more on the A types, but there are people who study other types too. Conjecture? Finite mutation type. So let's say example. This quiver. So now this doesn't come from triangulation of a puncture surface, but it's for any quiver, but now it seems that, so Grosek and Kilkantsevich proved this for all the quivers satisfying certain combinatorial condition, which is called the existence of maximal green sequence or something. And then I heard from somebody said that, so maybe considering cluster variety for all possible quivers is maybe not a good idea. And it's maybe only those quivers that appear in that theorem might be like the important. I think so, yes. For this one, Fook and Goncharov, they already sort of wrote down the canonical basis of this thing, enumerated by these points, without proof in 2003, in some small paper. And I think to prove this, at the moment, I think the only proof I know uses pretty heavy machinery, using some kind of categories, like some categorification. So in general, it's very hard to prove. But somehow this mirror symmetry gives you like magical statements, but not constructive. I think for this thing, it's barely computable. But in general, like you can't even write down one function, even for like smallest examples. Yes, but now they have some basis with no proof. You first have to prove that it's a basis. And then what I didn't say is that it must be a basis that satisfies certain number of properties. To prove them requires very heavy machinery. One of the properties is the structure constant positivity. So you multiply two basis vectors, and then you can write it down as a sum of other basis vectors. Because it's a basis, there must be coefficients. These coefficients are all positive integers. And that's something that's very hard to prove. And then each function written in each cluster chart are Laurent polynomials with positive integer coefficients. And then there's some more properties. And these properties are in general very hard to prove. I think even for this. By hand, you can't do.
Okay, any other questions, comments, days to have some more mathematical interactions. So let's thank Hyun again.
Thank you.